Okay, so welcome to our seminar today, our bi-weekly seminar. Today we have a special occasion because we have a guest here who has a long and illustrious history in work in rewriting theory, which of course is, if you look at it like that, one of the motivations or sort of paradigmatic examples from which graph rewriting was derived. So you could say, if you want to put it simply, that we took term rewriting and replaced terms by graphs. Obviously, if you do that, it turns out that it's not as simple as that, but this is one of the sources of inspiration for us, and one of the sources also of theories and theoretical questions that people have looked at over the last years, including sort of termination, confluence, and all these other things. Jean-Pierre Jouannaud is an expert, one of the main experts in this area, and so from that point of view, you could say he is a very well-informed outsider. But recently, he also started to get involved more deeply into the graph rewriting field himself, and in joint work with sort of our own Fernando, for example, and another sort of term rewriting expert, sort of addressing issues that have sort of interested us also for a long time, because they are very difficult, namely the compositionality and something that is very straightforward in term rewriting to build up derivations by composition, and quite difficult in graph rewriting because of the structure that is more complicated. So I'm looking forward to understanding how we can do that, and how maybe the history of term rewriting helps us in addressing that problem. So please, Jean-Pierre, stage is yours.
Okay, so thank you very much for your introduction. Before to start, I have to say that I got my first vaccine shot yesterday morning. And if you have not been vaccinated yet, I urge you to do so. So now we can move to the other stuff, to graph rewriting, composition-based graph rewriting. And this is joint work with Nahum Dershowitz and Fernando Herreras that I am talking about. I started this work several years ago with Nahum Dershowitz, and we had motivations at that time coming from mathematics, but I'm not going to talk about these motivations. Gradually, we got interested in graph rewriting per se, which was not the case at the very beginning. Therefore, my goal is to make you understand what is our line of thought in the area of graph rewriting. So, in a few words, our goal is to scale term rewriting to graph rewriting. So, it's very different, I believe, from the approach taken a long time ago by Hartmut Ehrig, where he started working directly on graph rewriting for various motivations related to graph grammars. Here, we started from term rewriting and have tried to scale to graph rewriting, and I will tell you how we do this scaling. So here is a little picture about term rewriting. So I have a term which I want to rewrite, and to rewrite it, I decompose this term in a context C, the left-hand side of rule L, and the substitution sigma. This is the basics of term rewriting, and C and sigma, of course, are computed at matching time. So we match L at some position in the term to be rewritten, which gives us C, the position gives us C, and the matching gives us sigma. And then we rewrite by replacing L by R. So in this view of term rewriting, the context and the substitutions are two very different objects which are manipulated separately. But now I will put them together instead. And therefore, I build something which I called an extension, which is made of the context C and the substitution sigma. And I compose this object with L in order to get the term to be rewritten. So I draw, you can see red arrows. So these red arrows relate, for example, the variables of the context, well, the one variable of the context with the head of L, and they relate the variables of L with, of course, the various heads of the substitution. And then putting things together, we call it composition. And therefore, it applies already to the case of terms. But now, excuse me, now if we have DAGs, the picture becomes, excuse me, becomes a little bit more natural in some way, because you may already have arrows from C to sigma, because the context may share some sub-expression in sigma. And again, also the rule itself, the left-hand side may be shared from the context, and the rule may share sub-expression in the substitution sigma. So now it's no more possible already to separate the context from the substitution. It's more natural to have it as a single object. And of course, you have more arrows because of sharing. If you have graphs, then the picture should be something like this. Some context, left-hand side, and now the arrows goes from the left-hand side of the rule to the context, from the context to the left-hand side of the rule. But there is no hierarchy as here, okay? Here, in the DAG case, you don't have cycles. In the graph case, you can have cycles by following these red arrows and then going inside terms by following the edges. So what does it tell us? It tells us that we need multi-graphs because we have multiple arrows, and we need multi-root and multi-graphs. The roots will serve for the connections between the various objects. So these thoughts led us to the notion of drags. So what are drags? You have function symbols with arities, which are these colored blobs here. Variable symbols with arity 0, which are these little squares with colors. And a drag consists of, it's a graph, so you have vertices. You have, of course, a successor relationship, but you also, since it is a label graph, you have labels, but you have also roots and sprouts. So what are roots? Each vertex can be a root with some multiplicity. So there is a root function which applies from the vertices into natural numbers. Of course, it can be 0. Lots of vertices can have no root at all, but the function root R is total. Then you have sprouts, which are a subset of the vertices. And sprouts, unlike the internal vertices, which are labeled with function symbols, the sprouts are labeled with variable symbols, as in terms. So because the arity of the variable is 0, sprouts have no successor. They play exactly the same role as in terms. While for internal vertices, the number of successors is governed by the arity of the label. And now we say that the drag is ground if it has no root, no sprout. So this is an example of ground tree. Only function symbols labeling the vertices. This is an example of DAG. So now we can share. And this is an example of drag. So this drag has no sprout. We will have examples of drags with sprouts later, but it has roots. So if you go the blue vertex, it has a number of roots, which is, you can figure out, is small because the arrow is not very large. The red vertex on top has a bigger number of roots because it has a big red arrow coming in. And of course, there are cycles in this drag, arbitrary cycles. So now the main insight is to build operations on drags. So in order to build operations on drags, I will take two drags and compose them in some way. And these two drags will be required to be compatible. So what does compatible mean? It means as soon as a vertex is shared by the two drags, their successors are shared too. So if I have two compatible drags, I can form their parallel composition, which I denote D plus D prime. And this is just, you know, the drag obtained by making the union of the two sets of vertices. And of course, if one vertex is shared, it appears only once in the union. So a triviality is that parallel composition is associative and commutative. And it has also an identity element, which is the empty drag. And an important remark is that there is a monomorphism, of course, from D to D plus D prime. So you know what monomorphisms are in case D and D prime are ground drags, because then they are just graphs. If they are drags with variables and sprouts, I will give a little hint later about what monomorphisms are, morphisms and monomorphisms. Second operation on drags, so the first was parallel composition, the second is wiring. So here I have two drags, one on the left of the equal sign, one on the right of the equal sign. And in the left drag, I will wire by establishing a connection between the green sprout and the purple vertex. And this connection is figured out by a little dotted curve ending with an arrow on this big red arrow going to the purple vertex. So this big red arrow on the purple vertex indicates some number of roots at this purple vertex. Now, if I go back to the sprout, you can see that this sprout has two incoming edges coming from some vertices, which tells you that the red root going to the purple vertex must have two roots as well. Now, when I do wiring, the two green edges and the two red roots will fusion and become two green edges to the purple vertex. So in some way, I just move the green sprout along the small dotted curve until it reaches the purple vertex. And then the two roots of the purple vertex are eliminated. Of course, the purple vertex may have other roots, other edges. Nothing is changed apart from these two green arrows going to the sprout and the two red arrows, red roots going to the purple vertex. So then one more important remark. I don't see you anymore. Can you hear me?
Yeah. We hear you. We can hear you.
Okay, good. I don't see anybody, but it's fine. So now there is another thing which I need to explain, which is this big dots, red arrow going to the sprout. Then this figure out some roots ending up in the green sprout. These roots are transferred to the purple vertex, transfer of roots. So you see when you wire, you move the sprout to some vertex, you eliminate a certain number of roots at that vertex, so they must be present, and you transfer the roots coming to the sprout to the vertex. These are the things you do for wiring. So here we had a single wire, and sorry, and now I will show you a very simple thing, a very simple case where my left drag now has only one green sprout, one purple vertex. This purple vertex, and that's it. Now what happens? So the green sprout disappears and the purple vertex gets new roots. If the number, so the purple vertex here doesn't need to have roots because the green sprout has no incoming edge. So perhaps it had no root. You don't care. You can still wire. It's an empty wiring in some sense. And in case the green sprout has no root itself, then nothing has changed in the purple vertex. So sprouts, isolated sprouts with no roots, will play the role of identities for wiring. Okay, now instead of having one wire, I may have many. I will wire a lot of wires at once. So, but this is only possible if the set of wires has good properties. So I call it well-behaved. What does it mean? First of all, you need functionality. So if you have two wires, S goes to R, S prime goes to R prime, then S and S prime must be different. That's what it says. It's not spelled out this way. It's a contrapositive thing, but this is what it says. So you cannot find a sprout twice in a set of wire on the left. Then there is a multi-set injectivity. So it's not exactly injectivity, but it's multi-set injectivity. It says that, I'm just explaining you. It says that two different sprouts can go to the same vertex, provided there are enough roots. If there are two roots, two sprouts can be wired to that vertex. Three roots, three sprouts can be wired. Of course, you can have you may have three roots and wire only one of them. So this is the injectivity generalized to multisets instead of sets. Then there is a coherence condition. If you have two sprouts which have the same label, then both must belong to the set of wire or none. Moreover, if both belong to the set of wires, then they must point at vertices which generate equimorphic subdrags in D. So generate, I guess you can understand that the subdrag which is accessible from that vertex Equimorphic means copy of one another. Copy is not equality because you may have different vertices provided they are labeled the same. You may have different sprouts provided they are labeled the same. So equimorphic is really a copy, but you may have sharing, of course, inside both copies. And then the last condition is well-foundedness, which just says that W doesn't induce a cycle on sprouts, because of course I go from some sprout S to some root R, but R again may be a sprout because sprouts can be rooted. So then you can, R may appear on left and so on. So this shouldn't generate a cycle. So the relation, the use relation defined by these wires must be acyclic. And then we can apply this, because it's acyclic, we can apply them one after the other, starting from the one which is used by anybody, so that when you eliminate it, you get another well-behaved set of wires for the rest. So I will show you now on one little example. I have this on left, a drag, and the set of wires which I will use for wiring is X goes to Y, Y goes to H. So I must start by X because X is using Y. So I cannot eliminate Y because otherwise X goes to Y would have no meaning. So I have to start by X. So I move X to Y and I get the second drag in the middle. The remaining set of wires is Y goes to H. And now let's explain how I get this drag here. So X is moved to Y. X has two incoming edges. It will cancel the two roots of Y, but X has one root which will be moved to Y. So I get FJH which point at Y, and Y has one root. H had three roots, so it's keeping its three roots. And then I move Y to H. So I have three incoming edges to Y. They will cancel the three roots of H. So I will have one remaining root from H, for H, coming from the Y root. Then, of course, when I redirect the edges, F and J point both to H. And when moving Y to H, then the edge starting at Y will end up at Y, so it creates a loop. Same example again, but this time I wire Y to X, X to H. So when I move Y to X, I will remove one root of X because Y has one incoming edge, but I will move two roots and for Y to X, so X will have two roots. So it's almost the same thing as before, but X has two roots while Y had one root before. And now I move X to H. So I will cancel as before the three roots of H, and the two roots of X will be moved to H, and I will have the same loop as before. So the result is not exactly the same with this slightly different set of wires. Yet another set of wires. Now I move, now I move directly Y to H and X to H in any order. They don't depend on each other, so I can do it in any order. So here I move Y to H first. I get the second drag. I'm trying to understand what I wrote, but anyway. So I move Y to H. So the one root of X has disappeared, and X Oh, excuse me. I move x to h, y to h, excuse me. I move y to h. So y had one incoming edge, h has three roots, two are remaining, two are transferred, so now h has 4 roots. And j, of course, stands on top of h. Nothing is changed for x. Now I move x to h, so I will create the loop. And for the number of roots, 4 minus 2 makes 2, plus 1 makes 3. Okay.
Jean-Pierre,
So this is wiring.
Jean-Pierre,
Yes?
excuse me. There's a question on the chat. Question is, what happens with the 3? So maybe.
Which 3?
So there are 3 lines here. Yes, go ahead. Please ask a question.
You mean explaining the 3 right-hand?
3 at the top. Can you explain the 3 at the top? Well, so what is the meaning of 3 at the top? It's incoming edges. It's an incoming.
The meaning of the 3 is that there are 3 roots at h.
So what is the root? Is it the incoming? Oh. Are there incoming edges?
H has 3 roots.
I don't understand what is a root.
Okay, so let's go back.
Can you hear me?
Yes, I hear you. Here is the definition of roots. I have a function.
Yeah, I don't care with mathematics.
To natural numbers.
I don't care with mathematics. I want to understand the intuitive meaning of a root.
So sorry, does this mean that you can
recognize that voice? Intuitive meaning of a root is it means that connections is I have a 3. This is a potential for connection arriving at this vertex. Okay.
So is it? I guess there are 2 different possible interpretations here. One is that this is a number which labels the root, basically, so you can distinguish the different roots. And the other possible interpretation would be that you can connect 3 wires to this.
That's right. So this is the second interpretation.
Okay.
It means I can.
So I understood it like that. Okay. So I don't understand why the h is dropping to 1.
Why is it in the end, you mean?
Yeah.
Because as I was saying, each time I apply a wire, then the number of roots at the place where I go is decreased by the number of incoming edges from the place where I'm coming from. So let's look the very first wiring on top left. I move x to y. Then you see that the 2 edges from f to x and h to x will be connected to y. And this is possible because y has 2 roots. But doing these connections, these 2 roots will disappear. So now, but x has 1 additional connection, which is not used in this wiring, which will be transported to y. So y ends up with 1. And then doing the second step, y is moved to h. There are 3 connections from FGH to y, which will cancel out the 3 roots of h for establishing the connection. So, but the root of y is unused, so it will become a root for h.
Okay, now I understand. So it means there is a notion of valence, so incoming valence. It's not the degree of the node, it's something different. It's not the incoming degree.
You call it the way you like. So it's really roots. The number of roots is really the potential for connection. Perhaps it's called valence in other circles, I don't know.
Well, in chemistry, you call it valence. But,
okay. Well, it's a good analogy. I didn't think about it. Okay, so now I have explained wiring. Now I can explain composition. So,
well, wiring is quite complex. In fact, it's quite complex.
no, it's very simple.
Well, it's very complex.
I'm sure you are smart enough to understand it.
Are you sure you could not decompose wiring in elementary steps?
Okay, so in the first paper we had with Nahum Dershowitz, we had this operator called composition, which was a big operator that people said didn't understand. So we decomposed it into wiring operations. We had not figured out at that time that we could do that. Now decomposing wiring again, we do it because we define one wiring step, which is this. So wiring many steps is decomposed in wiring step by step, and composition is decomposed in terms of wiring and parallel composition as well. So I'm going now to the third operation, which we call cyclic composition. And cyclic composition will involve, so if you look in the middle of the slide, which is this equation written in red, we make cyclic composition of D and D prime with respect to key, which we call a switchboard, which is just a set of wire for the sum of D and D prime. So in order to do cyclic composition, we first do the parallel composition of D and D prime, or sum, and then we do what we wire with respect to the switchboard key. So a switchboard key is nothing but a special set of wires, because wires must go either from D to D prime or from D prime to D, but you cannot have wires going from D to D or from D prime to D prime. So this is what is a switchboard. It's a set of wires which go either from D to D prime or from D prime to D. And then we wire the sum of the two drags. Okay, so now we can show nice properties. It's commutative, associative. It has identities, and the product or cyclic composition distributes over sum or parallel composition, if you prefer. So we have a very nice familiar algebra for drags. Okay, so example of cyclic composition. So you can, if I go back to the wiring examples, at the beginning I had two connected components, and the wires, at least the first two, were going from one to the other. So I can make it directly into a cyclic composition of two drags. It's the same computation as before. So first example, second example, but no third example. Why? Because in the third example, it's not a switchboard, because Y goes to H, that's fine. X goes to H, no, it's forbidden. It's inside the same drag D. So this is not, the third case was not a switchboard. The first two were a switchboard. Okay, so I assume you have understood these three operations: parallel composition, wiring, and cyclic composition. The first and the third operation, of course, are most important. The wiring is just a way of breaking cyclic composition into pieces. So now rewriting. So what is a rewrite rule when you have drags? Remember or know that in graph rewriting, you have a problem of dangling edge. when you rewrite, you shouldn't have an edge going nowhere. So here, this will come out extremely simply by this red dotted curve on top, labeled eta, which goes from the roots of L to the roots of R. And eta is just a total injective function mapping the roots of L to the roots of R. It's injective in the multiset sense again, okay? So you have only to take care that roots are multisets. So injection are a little bit different from what they used to be in set theory. So L and R are arbitrary drags. L is called the pattern. Variables all have an occurrence in the pattern. Well, this is not so important, but people like it that way usually. And then so the totality of eta and the fact that eta maps to the roots of R ensures the absence of dangling edges. So now let's see how things go. So I want to rewrite a drag, which I have written by composition as a composition of a context drag C on the left-hand side L. So first thing, so here you see what composition is used for. It's used for matching in some sense. Okay, so we break a drag into two pieces by matching, and the relationship between these two pieces is just composition. So I have written a sprout Z in the context, which goes to a root R in the left-hand side of the root. And this is told us by the switchboard key, which sends Z to R. Key of Z is equal to R. And now I rewrite. Well, when I rewrite, I still have my context C, but now I have right-hand side R. And I will compose them, but it's no more exactly key. It's some key prime, because I have to tell how the roots of L and the roots of R match. And we know how they match. They match with the injective function eta. So key prime of Z, which is R prime, should be eta of R. But R is key of Z, so we have this relationship, key prime of Z is eta of key of Z. And this is the switchboard which should be used on the right-hand side. You have to compose the left-hand side switchboards with the injective mapping the roots from L to R. Okay, so given a drag computing C and key, we call it rewriting extension. So excuse me, this W should be a C. So a rewriting extension C key of a drag pattern L is exactly this, okay? So this is the drag extension. Everything which is not L is a drag extension. And in a drag extension, there are properties, of course. Well, when you compose, L should disappear. So all roots of L should disappear. All sprouts of L should disappear. And all sprouts of C which connect to the roots of R, of course, should disappear too. So roots of domain of eta are all connected, sprouts of L are all connected, extension variables appear only once. This is a linearity condition, okay? So these variables in the context, they appear only once. For terms, you have only one variable. And extension variables are all connected. Okay, and so this is in mathematics, is not so important, but still there is one thing which is important, which is the last bullet here. If you have a variable x in L, well, the sprout L labeled x in L, and the sprout labeled x in R, these two sprouts must be replaced by something which is in relationship, and something which is in relationship for us, it's equimorphism of the drags generated at those places. Okay, so if you connect x to a vertex in C here and another x with another vertex here, these two vertices in C should generate equimorphic drags, which means copies of one another. Okay, so this is a little, I don't remember why I had this example, but this is an example of rewriting. So I have a rule which is in red. Hxy goes to kxy. You can see that the rule has two roots. These incoming red arrows. I could have written one arrow with two written next, but here it was easier to do my cut and paste to generate two arrows because they are here. So I have this drag here, and then I match with this rule. To match with this rule, I will generate this context in blue, and the switchboard is in black. Okay. Now, if you look at what happens, these map to H, so yes, excuse me. These map to H, but you can see that Z has two incoming edges from F and J. So in the composition, these two incoming edges will cancel out the two roots of H. So we will really get FJ HAA because X is going to A1. So I call the vertex for the first A, I call it A1. And the vertex for the second A, I call it A2. So A1 goes in place for X, A2 goes in place for Y. And you can see that A2 had two roots, only one is used. So there will be one remaining root at A on the right A in the drag to be rewritten. Then I simply replace the left-hand side by the right-hand side. They have the same number of roots. The mapping you can infer left root to left root, right root to right root. So I don't spell out the mapping, of course. I just replace this red drag by this other red drag, and I compute the result, and the result we just replace H by K. Okay. So, example revised to see some little phenomena which occur in drag rewriting. So now, yes. So the upper part is the same. So matching is the same. I start with the same drag. Matching is the same, but you see, I have two roots on the right A, on the right blue A. I have two roots. So now I will map X to A2, which is second A, and Y to A2, which is second A. I can do that because A has two roots, and further, the A2 is the same as A1. Okay, they are equimorphic, it's just A. So what do I get then? Well, I have an extra A on the side instead of having the root pointing at the same A, which is the right successor of H. Now I have no root on the right successor of K, but I have an A standing there with a root. Okay, so can I do that? Answer, it's wrong. I cannot do that. Why? Because, well, these two A, one with one root and the other one with two roots, they are not equimorphic because simply one has one root and the other has two roots. They are not equimorphic. They should be exactly same drags. They are not. So this I cannot do. I can do the first. I cannot do the second. Okay. So now I will compare with term rewriting very shortly to show you something which will be interesting for Jean-Jacques, I guess, which is that in drag rewriting, we need a lot of control, or if you prefer, of memory management. So I assume I have the rule fx x goes to j. Yes?
So can you read my question? Can you have non-linear?
No, I don't. Can you spell it out?
Can you have non-linear right-hand side?
Yes. So here comes an example.
So what's
with
happening?
non-linear.
You're making copies, or you're making pointing to the same
You
graph?
will see. This is just you are asking me what I'm going to explain on that slide. So I have the rule fxx goes to jxx, and I need to give name to the vertices. So f is named f, j is named j, but in fxx, x is named s1, x is named s2, the second x x2, and in jxx the first x is s3, and the second x is s4. So now I consider the following terms. T1 is FAA, but A is shared. So I have two vertices, F and A. I can call them F and A, they are shared. Now I look at T2 is FAA with vertices F, and for the other two I call left and right, LR. T prime, exactly the same as T1, T2, T prime 1, T prime 2, but I use J instead of F. And the vertices, when needed for AA, I call them L prime, R prime. Okay, now I can rewrite T1 to T prime 1, no problem. I need an extension with a two-rooted vertex A. So T1, remember, is shared. So if I cat below F, I get an A with two roots. So this will be the extension, an A with two roots. And the switchboard will send S1 to A and S2 to A, same S3 to A, S4 to A. In both cases, it's possible because I have two roots at A. So I can rewrite T1 to T prime 1. Very similarly, I can write T2 to T prime 2. This time the extension drag will be two copies of A, each one being single rooted, and the switchboards are what you expect. S1 goes to L, S2 to R, S3 to, I can switch off, of course, S3 to R, S4 to L, or S3 to L, S4 to R. They are equimorphic here. I can switch them off. Now the question is, can I rewrite T1 to T prime 2 or T2 to T prime 1? Answer is no. I have to do memory management. So I'm trying here to rewrite, let me make sure, T1 to T prime 2. So T1 is not shared, T prime 2 is shared. So F of A, well, in order to to end up rewriting for J, I will need 2 copies of one of the A's because I will need equimorphic drags to match the 2 X's of JXX. Well, identical drags to match the 2 X's. So one of these A's will need 2 roots, but one of these A here, I have 1 root each if I cut. So first thing I will do is add a root to A. I can do that. I compose with a sprout which has 1 root and nothing else. Then the composition will add a root at A. So now I can match FXX, and the extension drag is a first A with 1 root, a second A with 2 root. X is sent to the first A, and the second X is sent to the second A. And now in the right-hand side, I can send both X's to the second A. What do I get? I have J with A, which is shared, but I have a leftover A, which of course is added to JA. So I wrote with plus. So you can see what I cannot rewrite directly FA not shared to JA shared. I have to add a root first, and then I have an A left over. So this means that drag rewriting is extremely careful about memory management. Memory management, you must make it explicit. It doesn't come for free. It's a little bit like linear logic, okay? So here, what I'm doing here is banging this A. I add a root to A. I add a new connection. It's banging the A. And here, well, I just want to drop this A, of course, eventually. So I need a way to drop things. So memory management must be explicit in drag rewriting. So finally,
so question.
There is one drawback. Yes.
So I understand you cannot garbage collect, but can you duplicate? So I do not see.
I have to do it explicitly. So I need to add an operator for garbage collect.
Okay, so that's what I thought, but I wanted just to understand. Okay.
Yeah. I need a specific operator for garbage collection.
No, but for duplicating.
Yes, I need, for duplicating, I well, an operator for duplication.
Okay, thank you.
So drag rewriting in this view is linear in the sense of linear logic. So now one last thing about drags. So a rule is a pair here, but in some cases at least, we would like to share some subdrags in L on R. For example, sharing sprouts, of course, but not only sprouts. We may want to share more than that. So we have a more general notion, of a rule which is just a single drag, D, on a partial injective map from the roots of D to the roots of D. Now the domain of this map defines the left-hand side. So the image of this map defines the right-hand side. Okay. So, and then we can share. We don't need to eliminate and recreate what is shared in the left-hand side on the right-hand side. Okay, so I will be very brief about unification, conference, termination. Termination, we generalize the recursive path order to drags. Unification, we design the square complexity propagation algorithm which marks pairs of corresponding vertices in two drags. And this is why it's square complexity, because there are only a square numbers of pairs when you have two drags, of pairs of one vertex on one side and one vertex on the other side. Local confluence, we have a generalization of US theorem, and here I can explain it extremely simply. If we have a drag which rewrites with two rules, L goes to R and J goes to R, which are drag rules, without overlapping, okay? Then D can be rewritten as a composition of a context C of L and J. I don't need to put parentheses, composition is associative. So now, if you use the rule L goes to R, you rewrite L to R, but J stays the same. If you use the other rule, you rewrite J to D, but L stays the same. And of course, you can rewrite the L on one side, on the J of the other side, and you will, of course, join. So an extremely simple proof for Hewitt's lemma. Of course, if you have an overlapping, then the D will be decomposed in a context composed with the most general unifier, unified drag between L and J. So extremely simple proofs of Hewitt's lemma or Hewitt's theorem, whatever. Okay, so this is a bibliography corresponding to these three works. First of all, TCS paper for a framework for graph rewriting, which is drags. However, in that paper, we didn't have wiring. It was a direct definition of composition, which was complex. And also, the roots were lists with repetitions rather than multisets. Then with multisets, the algebra is quite better. The second paper is the graph path ordering, and the third paper is unification and confluence, which is submitted, not yet published. So now we move to core. So what is core? Core, it's a name we choose for our method, composition-based rewriting. And the name is meant to suggest that, like DPO, it has potential to apply to various kinds of graphs, not only drags. So, and then of course, can we relate core with DPO in one way or another? And this is what I will briefly explain now. I have no idea about timing because I don't have a watch, and I can see the watch on my screen. So anyway, so first of all, we need to define morphisms. So of course, a drag has an underlying ground drag if you eliminate the sprouts and the roots. So you need morphisms to be graph morphisms as usual. And then you need to map roots. They are mapped to roots or edges, because a root is a potential for an edge. When you map it to define morphism, you can map either to root or to existing edges. And then there is a condition again where equimorphism pops up. Equimorphic subdrags must be mapped to equimorphic subdrags. So for example, you cannot map a variable x of a drag. Well, if you have two x's, if you have two x's in a drag, they must be mapped by a morphism to two y's, not to one y and one z. Or they must be mapped, of course, to f and y of y and f of y, two different f of y's, but not to f of y and f of z. So you must keep relationships between variables in morphisms. And of course, a monomorphism satisfies injectivity. So you have injectivity for the ground part, the slide has evolved. The 2, I forgot to eliminate it, and you have a condition for sprout root injectivity. We just succeeded to capture by one condition both injectivity for roots and sprouts. So I don't detail what they are, but basically it says there is enough room to do the morphism injectively. So now we have a first result which is important because it was asked to us before by some DPO people, by some German DPO people, of course. So this result says matching and with respect to composition and matching with respect to monomorphisms, as in DPO, coincide. So there is an extension E key such that D can be rewritten del composed key with E if only if there is a monomorphism H from L to D. Okay, so here composition is the way we express matching, and in DPO existence of a monomorphism is the way they express matching as well. So both notions coincide exactly. Well, okay, then we try to apply well, DPO applies to categories of graphs which have graphs as objects and morphisms as arrows. So can we build a category of drags? It's known that there are some difficulties already to build categories for terms. Okay, but these difficulties can be gotten around, but by moving from adhesive categories to M-adhesive categories, but here it doesn't work. So we have counterexample to adhesivity using either drags with roots or non-linear drags. Okay, so at least what this means is that the natural way of defining morphisms and monomorphisms on drags do not lead to categories which have good properties. And the property which breaks down systematically is the Van Kempen property. So, at least it's not easy to build adhesive categories of drags. Then, however, if we eliminate roots and eliminate linearity, non-linearities, then we have an M-adhesive category. So we can use DPO on drags that have no roots and no different sprouts labeled by the same variable. Of course, if there are no roots, you cannot establish connections. So you better take the ground drags directly, and that's the conclusion of this. So DPO applies to ground drags. Non-linear rules are not expressible in DPO. So I think this is a major way in which DPO is limited, which is linearities, non-linearities. Okay, now let's go the other way around, trying to do core with arbitrary graphs. So to do this, I introduce a core graph. So a core graph is a tuple where I have a graph J, and I have sinks which are vertices without successors. So some of these vertices I declare them to be sprouts, and I will label them with variables. And then I add roots to arbitrary vertices in the graph. And I have a core graph. So the vocabulary is not so important. So you understand what is a core graph. I just turn things into some of things into sprouts, and I add roots wherever I like. Now we have shown that the core method applies to any category of core graph such that its objects are decomposable, which means if you have two core graphs D and L as objects in the category, and you have a rewriting extension E key such that D is equal to L composed with E, then E must belong to the category, must be an object in the category. So it's a closure property of the object in the category, and we call it the complement, of course, and it has a rather direct link with push-out complements in the category of graphs. Then we also we don't only need to match the left-hand side, we need to build the right-hand side. And then we need a property we call composability, which is that if D and L are graphs in the category and we compose them, we need to obtain a graph in the category. And for composability, we can, of course, go back to parallel composition. So the objects must be closed by parallel composition, but this is very natural. You take two graphs, you put them as two components of a bigger graph, and you have a graph in the category. This is very usual. And we need also to show that varying generates a graph in the category. Implies composability. So varying says we just move a sprout to another vertex, taking the edges along and cancelling roots. Of course, you have to express it in terms of objects in the category without sprouts and roots, but I think this is again an extremely natural property for a category of graphs to have. So can we apply core to other categories of graphs and drags? Answer is yes, and here is an example which is simple. It's the example of simple graphs, that's why it's simple. And we know that simple graphs, DPO doesn't apply to simple graphs because they are not M-adhesive. So what is a simple graph? On the ground part, you have at most one edge between two vertices. That's a simple graph. But now you have also roots and sprouts. So the definition I take for simple graph is that a vertex cannot be a root more than once, either 0 and 1. I can put one root exactly, no more. Sprouts cannot be root. And then if you follow a path to a sprout, you cannot have two rooted internal vertices successively. So this is the definition I take for core graphs. Of course, simple graphs. I have the liberty to choose it, of course. And then I can show that the category of core simple graphs is composable and decomposable. So I can do core rewriting on simple graphs. Now, for the general case, we have conjectures, but we are working on it, so it's not finished. So the conjecture one says, if the category of graphs has pushouts and pushout complements, identity extension morphism has pushout and pushout complements, that imply composability, decomposability of the class of core graphs. So what are identity extension? If you have a morphism from D to D prime and extend by composition to a graph E, then what is in E, you will map from the left E to the right E by identity. That's what are identity extension morphisms. So we have good progress on this conjecture, but it's not finished. And then we have a conjecture 2, which is that assuming a category of graphs which is adhesive or M-adhesive, then we can define an abstract notion of composition on the objects of the category. So here, no more variables, no more sprout. It's an abstract notion of composition defined in terms of pushouts and pullbacks. And once we have defined this abstract notion of composition, then again, composition-based rewriting applies. So these are two conjectures in which we believe strongly, but it's not yet proved. And I think this is the last slide. Thank you very much for your attention, and I'm ready for taking many questions, in particular from Jean-Jacques.
All right, thank you very much. Jean-Jacques, do you have a question? Anyone else has a question?
Well, I am obliged to ask a question.
You are allowed to, yes.
No, I am forced. What can I say? I did not understand what is composition. I'm sorry. Oh, I have another remark. What you call chi is a xi in Greek letter. Okay. So chi is not xi. It's different.
This is key. This is key, right?
No, xi.
No, it's xi.
Xi. Xi in French. Yeah. Xi.
Yeah, right. Xi. It's xi.
Oh, that's for future talk. I'm
but
sorry.
It's hard to pronounce xi.
But going back to composition, can you just
yes,
flash the slide on composition? Okay, so where is
here.
Composition?
That's composition here. The red
there was a definition of composition, no?
So
where is the definition?
The red equation is the definition of composition, yes.
Oh, I see. So so my last question, because I don't want to monopolize everything.
Yes.
So I did not get what was the well-foundedness property. So can you come back to that? That's at the very beginning.
Yes. So very simple. Take this example here. Top one, X goes to Y, Y goes to X, Y goes to H. If I had X goes to Y, Y goes to X, it would not be well-founded. Cycle among variables. Okay? So this is well-foundedness. W does not induce a cycle on sprouts.
So on sprouts. Okay, on sprouts.
Yeah.
So can you show the example again?
Sprout.
Next slide. Sprout, they are, so what are the sprout here? X and Y. Okay.
Well,
so,
X and Y are sprouts. Yes.
Okay, I understand.
So I follow the variable and I never generate a cycle.
But is the order in which you take the wires is relevant or not? Because why did you start it with X and not with Y?
So, okay, if I start with Y, then I move, in the first case, right? This case, if I start with Y, I move Y to X, and then I need to move X to Y, but Y has disappeared. I cannot do it anymore.
Okay, I see. That's the only reason, is it?
Yes, that's the only reason.
Okay, thank you.
All right, thanks. Any more questions from anyone else?
Yeah, I have one.
Okay, yeah, go ahead.
Hi, Jean-Pierre. Thanks for the interesting talk. Just on the definition of drags, you have the successor function, which assigns a natural number to each node, which is the number of out edges. And well, that means, of course, if I want graphs with an unbounded number of out edges, I guess I would have to resort to infinite signatures, and which in turn might mean infinitely many rewrite rules and so on, which is not so nice. So my question is, if you would allow to have an arbitrary number of successors, would that in any way impact on the theory, or what you think everything would go through?
Of course, it impacts the theory, and then I would have to go to the more general theory we are trying to building up, where we have other categories of graphs, including then graphs that may have infinitely many successors at some vertices. So
I didn't
that's
mean
the way it impacts.
I didn't mean infinite.
General.
I just meant unbounded and arbitrary. Yeah.
Oh, unbounded.
Yeah, unbounded.
Then I have two ways to do that, okay? I have two ways to go to unbounded. A first way is by having a binary function symbol, which is associative, and then using associativity, it's basically unbounded. So I would need to define a drag rewriting modulo associativity, and then you would get into the difficulties of rewriting modulo, of course. But the other way, the other way, but by having unbounded, means there is no arity at all, right?
Sorry, my question really is in the definition you are showing here for successors. If you just drop the equality there in the under successor, so it's just a mapping from V to V star. Any out sequence is allowed. Would that be a problem for your theory?
Well, I didn't think about it, so.
Because that's one way of ensuring you have an unbounded.
Yeah, I understand.
And the background is kind of, and I know you may not think about classical graph algorithms in the first place, but many graph algorithms are known to be more efficient if you can you assume that your graphs have bounded degree. So
well, I know that. I know that.
Yeah.
Many become polynomial instead of NP.
Yeah. For instance, yeah.
Yes.
Okay. Anyway, so it's just a comment, observation, or question. Yeah, you can think about it anyway.
So yeah, I cannot comment more than that because
I understand. That's
we
fine.
haven't tried. We haven't tried.
Okay. Thanks.
Okay. Any more questions? So there's a question here from Fayan. Fayan, do you want to ask that yourself? Unmute yourself and ask that.
Yes, I managed to unmute myself. Hi, Jean-Pierre.
Yes.
At the end, you were talking about categories in which you were doing composition-based rewriting.
Yes.
That is a nice approach. Do you think, is it possible to find a categorical condition that then guarantees the confluence of that composition-based rewriting?
To guarantee confluence, you mean?
Yeah.
I have no idea. Okay, I have no idea. If I take the conjecture one approach, then I have graphs with variables, and then I can use unification algorithms to decide, to try to decide if it's decidable confluence. If I use this other approach, then you will get, I think, you will get exactly the same difficulties as presently with DPO, where when you try to define what are the overlap, what is a good notion of overlap for two graph rewrite rules. So my own way of doing that kind of things, I would rather take the core graph approach to analyze confluence for arbitrary or for other categories, like if possible, but I would try. So perhaps a good thing would be to try it for simple graphs, since I know it works very well for simple graphs. I can try for simple graphs to check if confluence is easily decided.
Yes, you would hope that that is possible somehow.
I didn't hear.
You would hope if your definitions are the right ones, that such results become possible.
I hope so. They are the right ones, but of course.
Yeah, but then getting this kind of confluence results, that is a proof that you're doing the right thing.
Yeah, perhaps. I hope so.
Yeah, nice.
Okay. Fernando raised his hand. So Fernando, do you want to add something? Unmute yourself and.
Yeah, I was just making a comment with respect to this question. So if you take, we studied, and actually Jean-Pierre mentioned the paper in his presentation, we studied confluence for drags. And in a way, the way of finding whether some rewrite rules for drags are confluent or not are in a way a generalization of term writing, confluence of term writing. So you build critical pairs by unification of the left-hand side of drag rules. If you go to arbitrary categories, so one of the approaches that we are looking at for generalizing this kind of approach, this core approach, is by going into general categories, and in there, well, you have some conditions in order to ensure that you have a graph rewriting, which are obviously related to adhesivity, but are not exactly the same. You don't need all pushouts as you need in all pushouts along morphisms as you need in adhesive categories. You need only some pushouts of this. This means that this is the reason why the approach works for simple graphs that is not an adhesive category. In there, we didn't study confluence at all, but I guess that more or less it would be very close, if not very similar, if not similar, equivalent approach for checking a confluence, like what can be done for DPO with interfaces, graph with DPO for graphs with interfaces, because you can see that that core graphs are a special kind of graphs with interfaces. Interfaces are special in this case because they are not the interfaces are not arbitrary graphs, but a special category, a special subcategory of the category of graphs. And I guess that the constructions that critical pairs for graphs with interfaces would more or less apply here, which means actually that critical pairs for DPO transformation without interfaces, it would be very close, if not the same thing. A different question is that we guess that as with DPO with interfaces, confluence is decidable in case of termination. Probably it would also be decidable here.
So okay. I can make a more precise comment that I made before about confluence. And this is what I explained before. If you have two non-overlapping graphs, so core graphs, say, then you will be able to write your entire graph in the form D equals C, which is context, composed with L, composed with J. So this, you get it as soon as you have a composition, which is associative. That's all you need. You need a composition associative, and you will always be able to write it this way. So then you can immediately prove that confluence relates to critical pairs, so to the case where L and J have common vertices when they are put on top of one another. And therefore you relate this directly to unification of core graphs. So as soon as you are in a category where you can unify core graphs, not graphs, but core graphs, then you have confluence. You can decide confluence very easily. And I believe that even with the other approach where we define composition directly, abstractly in the category, then we still will have this equation here. Okay, so this composition operator, I believe, allows us to address the confluence problem in an extremely neat way. Of course, if you don't have variables, so if you have ground graphs, if you don't have variables on sprouts, I may guess that you don't have nice ways to express what we usually call most general unifier. Because to express most general unifier, you need the variables that make the unifier grow and grow. Actually, here the unifiers, they grow by composition, and we can, in the same way we can compare unifier, or we can compare substitution. Here we compare context extensions by composition. This is the way to compare. When we compose two different context extensions, we get a bigger one. And we can show that getting smaller is well-founded. So this is why we have notions of most general unifiers. So I believe that having variables allows one to get a clear, compact notion of most general unifiers, or perhaps several most general unifiers, while when you don't have variables, you turn out to define other notions on the ground objects, and these other notions, they are not as compact as most general unifiers. So that would be my guess. So and that's something we may look at in the future, except that the future becomes smaller and smaller for all of us, especially me.
Okay. Well, thank you very much for that. I suggest that we close the public part of this seminar now. So we switch off the YouTube channel and continue this in a private Zoom session where we can continue asking questions or just chatting. So thanks again, Jean-Pierre, and everyone who attended and asked interesting questions and so on. And yeah, I let.
Well, thank you for inviting me. It was a very good opportunity to talk about this work.
Yes, and just to clarify, we stay here in the meeting with everybody who still wants to discuss, and then we can also switch on the camera.